All right, so section 10.5 is on permutations and probability. So we're continuing chapter 10. We just took a test on 10.1 through 10.4. So this is the next logical progression. So we'll define permutations and we'll see how they are different than probability, but also how they are used to find probability. All right, so this is just a review question, but it leads into permutations. So you may not need to write it down, just pay attention, and it should make sense to you already. So it says how many outfits? Use a tree diagram to find how many different outfits you can make. If you have 4 sweaters, 6 pairs of pants, and 2 pairs of shoes. The tree diagram is, for the most part, done for us already. It's incomplete, and that's just because it would be very large if it was totally complete. But it's done enough that we can understand what we would do. So our first decision would be, what sweater are we going to wear? Well, we have 4 different sweaters to choose from, and that's why you see 1, 2, 3, 4 different branches for our choice of sweater. Now, once we've chosen a sweater, next we have to choose, well, what pair of pants are we going to wear? And there are 6 pairs of pants. So from each branch, each sweater branch, we would have 1, 2, 3, 4, 5, 6 different choices of what pair of pants we're going to wear. Once we've chosen a pair of pants, we now have to choose a pair of shoes. And we have 2 pairs of shoes to choose from. So from each pants branch, we have 1, 2 different pairs of shoes. So by the time we choose our sweater and we follow that sweater branch all the way out to the end, we have 1, 2, 3, 4, 5, 6, 7, 8, these aren't matching up exactly, 9, 10, 11, 12, right? Let's do it like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different outfits that can go with that single sweater, right? Well, if we have 12 different outfits for that single sweater, then we would have 12 more outfits if we followed this branch all the way through, and we'd have 12 more outfits if we followed this branch all the way through, and we'd have 12 more outfits if we followed this branch all the way through to the end. So altogether, how many different outfits? 48 different outfits. Now we've figured this out using a tree diagram, which we used a lot in the previous 10.1 through 10.4. But we don't have to use a tree diagram all the time. And that leads us into what we're talking about today. The counting principle. The counting principle says the number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each thing can occur. Sometimes you'll hear the counting principle be referred to as the fundamental counting principle, or abbreviated FCP. Let me show you how the counting principle works for our previous example. So we used a tree diagram. Instead of taking the time to think through and draw out this tree diagram, which would be pretty complicated by the time you drew the whole thing, let's use the fundamental counting principle. We take the number of sweaters, 4, times the number of possible pairs of pants, 6, times the number of possible pairs of shoes. And we multiply these together, and it will give us the total number of possible outfits, or the total number of possible outcomes. Well, 4 times 6 is 24. 24 times 2 is 48. There's no question that that's a whole lot easier, right? Yeah. So the fundamental counting principle, you take the number of ways in which each thing can occur and multiply them together to find the total number of possible outcomes. And this is going to be crucial in probability, which you'll see here as we go. All right, so we're going to apply this fundamental counting principle to a few more problems, a little bit of practice. It says, suppose a set of license plates has any 3 letters from the alphabet followed by any 3 digits. How many different license plates are possible? Okay, well, this makes sense. Every car has a different license plate, right? So the state of Pennsylvania needs to know how many license plate numbers do we need to have, right? We have X number of cars, we have to have at least X number of license plates. And they need to make sure they have enough. So this is very practical math. Now, what I like to do is I like to use boxes. So the first 3 parts of the license plates are all letters. So I'm going to use these boxes to represent the 3 letters that start out a license plate. Then usually there's like a dash or something on a license plate. And these 3 letters are followed by any 3 digits. So I'll do 3 more boxes, 1 representing each digit. And this is just sort of like a visual way for me to see the problem. Now, they don't tell me that I can't repeat letters, and they don't tell me that I can't repeat digits. So for this very first letter right here, how many different letters could go there? 26. There are 26 letters in the alphabet. Any one of those letters could go there. Since they didn't tell me I can't repeat letters, then any one of the 26 letters of the alphabet could also go there, and any one of the 26 letters of the alphabet could also go there. Right? We're in the process of taking the number of possible outcomes in each place, and then we're going to multiply them all together, right, with the counting principle. All right, so this box, this is our first digit. How many possible digits? Well, we know only 1 digit could go there, but how many different digits could go there? Not 9, but 10. 0 through 9 is actually 10 different digits. So 10 could go there. We can repeat digits, so any of the 10 could go there, and any of the 10 could go there. Now, using the counting principle, let's multiply all of those together to find out how many different license plates we can come up with. So we multiply these together with the counting principle, we get 17,576,000 different license plates that you could come up with here. All right, let's do part B because it's a little bit different. Now it says, what is the probability that a license plate has no repeated letters or numbers? All right, the first thing to figure out here, or to recognize, is that this is a totally different question than Part A. Part A asked how many different license plates are possible. Part B is asking, what is the probability? This is one of the most important things when you're doing probability problems, is read carefully and know what they're asking. Right? You don't know how many times I've seen students calculate a probability when they're asked to find how many different of something there is. Or they calculate how many different of something there is when they should be calculating a probability. Okay, so read carefully. Now, we know from our previous study that probability, let me write this out for a refresher, the probability of an event happening is equal to the number of ways to get a desired outcome over the total number of possible outcomes. This is the fundamental formula for calculating probability. Now, we applied this formula to this specific example. We want to find the probability of getting a license plate with no repeated letters or numbers, right? That's our event, a license plate with no repeated letters or numbers. So we're going to have to find the number of ways to get a license plate that has no repeated letters or numbers over the total number of possible license plates that you can get. Well, we've actually already calculated the denominator of this fraction in part A, right there. There's the total number of possible license plates that we can get. So we already have that piece. We have to calculate the top of this formula, the top of this fraction. How many ways can we get a license plate with no repeated letters or numbers? So let's do that. How many ways can we get a license plate with no repeated letters or numbers? We have to apply the counting principle again. We're sort of taking a step back. Even though the question here is what is the probability, we actually have to calculate a counting principle problem first before we can calculate the probability. So if we apply our boxes, we have the same setup. Letters, 3 letters, followed by 3 digits. But now we cannot repeat letters or numbers. So the first letter could be any of the 26 from the alphabet. But once the one letter goes there, you can't use it again. So now there are only 25 letters left. And once a letter goes there, you can't use it again either. So now there are only 24 letters left to choose from. For the first digit, you can choose any of the 10, but once you choose one, you cannot use it again, so now you only have 9 to choose from. Now you can't use that one again either, and which means you only have 8 to choose from there. With the counting principle, we're going to multiply all these numbers together, and we're going to find out how many different ways we can get a license plate without repeating letters and numbers. So using the counting principle, we come up with 11,232,000 different license plates that do not repeat letters or numbers over the total number of possible license plates we can get, which we found in part A. And if we want to represent our probability as a decimal, we can divide these two numbers. And we get 0.64 rounded off, which is approximately 64% of the license plates will not have repeated letters or numbers. So the big takeaway from this example is, and I said this previously, is the part where we had to use the counting principle before we could actually find the probability. Okay? In the first part of chapter 10, 10.1 through 10.4, you were dealing with basic probabilities. You were using that fundamental formula, but you basically were given the numerator and the denominator. Now, in this case, we had to calculate both of these ourselves before we could put them into a probability. Okay. All right, next is a factorial review. So this is sort of a side note. We're going to need these skills to deal with the probabilities, but it's not calculating probability itself. So you learned about factorials way back, maybe middle school you started, but we probably need to refresh. So it says evaluate without using the factorial function on the calculator. And number 1 says 5, and then it has this exclamation point. Well, that exclamation point in math means factorial. And you might remember that factorial means that you take the number, like in this case 5, and you multiply it by every digit less than it all the way down to 1. So 5 factorial, let's see, 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120, 120 times 1 is 120. So 5 factorial equals 120. And I'll show you how to do this on the calculator in a second. It's very simple. Now number 2, 9 factorial, well, same idea. 9 times every digit less than it all the way down to 1. So 9 factorial is 362,880. Okay, so the next one, though, is actually a little bit tricky. 0 factorial. 0 factorial is kind of interesting. There's no numbers less than it down to 1. 0 factorial always equals 1. And there's a math explanation behind this, but we're not going to get into it right now. Just remember that 0 factorial equals 1. Okay, things get a little bit bigger and harder maybe. So number 4, 3 factorial times 4 factorial. Understanding what this means, 3 factorial is 3 times 2 times 1 times 4 factorial, which is 4 times 3 times 2 times 1. So we would just multiply all these numbers together. 3 times 2 is 6. 6 times 1 is 6. 6 times 4 is 24. 24 times 3 is 72. 72 times 2 is 144. 144 times 1 is 144. Oh, there we go. Now we could also do this very easily on the calculator. Let me show you. All right, 3 factorial times 4 factorial. 3 factorial. Hit the math button. Go over, let me find it here. Over to probability, P-R-O-B. Down to number 4 is the factorial, the exclamation point. So 3 factorial times 4. Oh, I have to hit the math button. Probability, number 4, 4 factorial, enter, 144. Simple enough, right? Okay, number 5, 26 factorial over 21 factorial. So obviously we could use the calculator. That would be the most efficient way, and that would be perfectly fine. But I want you to understand what is happening here. 26 factorial means 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19, 18, 17, all the way down to 1, right? Divided by 21 factorial. Okay, well, we know that means 21 times 20 times 19, 18, 17, all the way down to 1, right? Now look at what's going to happen. We can cancel out the numbers that are the same on the top and the bottom. In this case, 21, 20, 19 on the bottom, 21, 20, 19 on the top. All of this cancels out with all of this. So to find our answer, we could just multiply these together. $7,893,600. And we could have done that on the calculator very easily by typing in 26 factorial over 21 factorial. Good. All right, last one, number 6. 500 factorial divided by 499 factorial. All right, those are some big numbers. We better do this on the calculator. 500 factorial, let's hit math. Go over to probability. Number 4. 500 factorial divided by 499 factorial. Math button, over to probability. Number 4. Enter. overflow. Calculator can't do this problem. The calculator cannot do this problem because these numbers, 500 factorial and 499 factorial, way too big. It's overflowing the calculator. So we need to understand number 5 in order to do number 6, right? Let's write this out. 500 factorial, 500 times 499 times 498, all the way down to 1. 499 factorial is 499 times 498 times all the numbers down to 1. And then we can cancel out the ones that are the same on the top and the bottom. And our answer is just sitting there nice and pretty, 500. Kind of interesting that the calculator can't do such a simple problem. All right. Finally, we get to the actual topic of today's lesson. Permutations. A permutation is an ordered arrangement of items that occurs when no item is used more than once and the order of arrangement makes a difference. The formula for calculating permutations, the number of permutations of n objects taken r at a time. That's how we say that. The number of objects, of n objects taken r at a time equals n factorial over n minus r factorial. So let me explain this formula. First, let's start with this NPR piece right here. N objects taken r at a time. Here's what this means. If you have a group of objects, let's say you have like 10 objects, and you're trying to figure out how many different ways can you arrange 5 of the 10 objects, then n would be 10, your total number of objects, and r would be 5, the number that you are taking away from the 10, or the number that you are actually using out of the 10. In this NPR, the n is always bigger than the r. The bigger number always goes on the left, and the smaller number always goes on the right. Now the actual formula piece right here, you can see why we just reviewed factorials, because there's factorials in this formula. But let me calm your nerves. The calculator can do this stuff very easily. You should have this formula written down. You should understand it. But most likely, you're going to use the calculator for most of your calculations, which is perfectly fine, okay? All right. One last important piece of information on this slide. All permutation problems are also counting principle problems. Okay, so we're tying these two things together. If you are asked to find how many permutations of something there are, you could either apply this formula, which, as I said, you would use the calculator, or you could apply the fundamental counting principle, where you multiply the number of objects in each piece of it and multiply them together. So this is a very important note to remember. All right, so I'm going to show you how to use the calculator to calculate the number of permutations. In this case, they're asking us to calculate this right here. So this 9p4. Notice the numbers are smaller, right? Those are subscripts. The p is bigger. So what this means is if we have 9 objects, how many different ways can we arrange 4 of those 9 objects? Any 4 of the 9. That's what we're trying to figure out. How many different ways can we arrange any 4 of those 9 objects? Well, let's pull up the calculator. 9. So once you have your 9, hit the math button. Go again over to our probability. And number 2, right there, is our permutation formula. So hit enter, and all of a sudden that pops up. Oh, actually, here, now I got to put the 9 in. Depending on your software, you might need to put that 9 in first or after you choose the permutation function. And then I put the 4 in on that side, and I hit enter. 3024. So what this means is that if I have 9 objects and I'm trying to figure out how many different ways I can arrange any 4 of those 9 objects, there are 3024 different ways to arrange any 4 of the 9 objects. We could have used the formula. We also could have used the counting principle. Let me show you how we would have used the counting principle here. We want to arrange any of the 4 9 objects. If we have 9 objects to start with, any of the 9 could go here, but we cannot repeat. Remember, that was the first characteristic of a permutation. So now we can choose any of the 8 that are left, any of the 7, any of the 6. 9 times 8 times 7 times 6. 9 times 8 times 7 times 6. 3024. Permutation using the formula. Permutation using the counting principle. So here's our example. 7 flute players are performing in an ensemble. Part A says the names of all 7 players are listed in the program in random order. What is the probability that the names are in alphabetical order? So remember I said the most important thing to start off is, what is the question? This is a probability question. So we're going to use that fundamental formula, the number of ways to get the names in alphabetical order over the total number of ways to list the names. So think about it. If you have 7 names, how many different ways can they be listed in alphabetical order? So there is only one way to list these 7 names in alphabetical order. That's going to be the top of our probability fraction. Now the next question is, how many different ways can we arrange the 7 names? Well, now we're talking about a permutation that we could either use the formula or we could use the counting principle. Right? If we wanted to use the counting principle, we could do 7 boxes. Any of the 7 names could come first, then any of the 6, 5, 4, 3, 2, 1. Let's find out what that is. That's just 7 factorial, right? (5,040) different ways. So the probability that these names are listed in alphabetical order is 1 out of 5,040. Part B says, after the performance, the players are backstage. There is a bench with room for only 4 to sit. So we have 7 flute players, but only 4 of them are going to be able to sit down. How many possible seating arrangements are there? How many possible seating arrangements? This is not a probability problem. This is a permutation problem. How many different ways can we arrange these 4 flute players, right? Well, out of 7 flute players, we want to find out how many different permutations there are, or how many different ways we can arrange 4 of them. Use your calculator function for permutations, 7p4, 840 different ways that we could arrange 4 of the 7 flute players on this bench. finally, part C, what is the probability that the group of 4 players is sitting in alphabetical order? What is the probability? So this is a probability problem. So let's use our fundamental formula. How many different ways can they be arranged in alphabetical order? The 4? One way, right? Out of how many total possible ways could these 4 flute players be arranged? 840. There's our probability.